So let's talk about searching. Searching is a process of finding out a particular element in a list of n elements. So this list, we know we have learned about different lists, right? So one such list is arrays or linked lists, or it can be a hash table, or it can be a tree or graph, right? So we have learned about these data structures. So today we are going to talk about a particular problem. We are given a sorted array and we have to search for this number 33 and return the index where 33 is located, right? So this is an important thing. You see you have an array and it's a sorted array. So if I want to do this, like solve this problem, the first thing probably I will do is, that's the most intuitive thing. I will start at the beginning, right? And keep on searching. So I will keep on searching. And you see, after a few searches, I will find 33 and then I can return 4, right? So that's simple. So this is called, what we are doing here is called the linear search. In a linear search, we start at the top of the list and compare the elements there with the key. If we have a match, the search terminates and the index number is returned. Okay. So for example, if my search was like search for, say, instead of 33, if someone say like search for 97, in that case, I had to go all the way to the end and to find 97 and then return 14, right? Return this 14. And what is the time complexity for that? As we said, like this list, this is an array as n elements. So in the worst case, I have to look for all the elements to find my my searched element. So the time complexity is order of n, right? Now, array has two very good capabilities. So one good capability of array is the random access. So you know all the indices and you can actually directly jump to any index, right? So if you want to go to index 10, you don't need to start at the beginning, right? And go all the way to 10. Like in a linked list, obviously you have to start at the beginning, but this is an advantage of an array. So how can we use this advantage of random access of array to make this search even faster, right? So there comes the binary search. And the binary search is a divide and conquer algorithm. Already you know what divide and conquer algorithms are. And the more interesting thing is, all of you are already doing binary search in your daily life. So for example, say you are looking up for a word in a dictionary. And the word that you're looking for is a manage. You want to find this word manage. Somehow you want to look for this. So do you start at the beginning of the dictionary? Do you start at page 1? No, right? Because why don't you look it up at page 1? Because you already know that, hey, it's not going to be in page 1 because page 1 is going to have all the words starting with A, right? Do you go to the last page? No, you don't do that, right? Because you know that the last page has the words with Z. Okay, so where do you look? So you try to find the words that are with M. So what you do is, M is roughly in the middle in the alphabet. So you go to the middle of the dictionary, right? So you go to the middle of the dictionary. And if you're very lucky, you will find the word manage at that very page, right? But if you don't find it, say you don't find it, and you ended up at a page which has words with, say, O, right? So what you do, you just go to the next. What you do is you search, you go back a few pages, right? Because the M is in the back page, a few pages in the back. Otherwise, say you go to check the middle and you find the words with, say, K, right? So what you do is you go forward, right? So so do you see that how you are using this divide technique? instead of just starting from page 1 or going to the end, you just roughly start in the middle. So you divide the problem, and then once you know that, okay, you end up somewhere, say you end up at K. So now you just discard the whole back half of the dictionary, and you just look for the forward part, right? So this is how binary search works. So let's see how we can use it for our previous problem. So binary, if I want to binary search for 33, I know that my low index is 0 and the high index of the array is 14. I know the size of the array. So I just go to the middle. So the middle index is 7, right? So I can just, since I know the index and I can do a random access, I can just look for the 7th index and see what is the value. So the value is 53. 53 is larger than 33. What does it mean? It means that nothing here on the right side can be, 33 cannot be on the right side. Simply as simple as that. Okay. So can we see that initially my problem space was n, right? So the problem space was n, and now the problem space has reduced to n over 2. So the problem space has reduced to n over 2. That means the only place that I have to search is this half, right? So next, I know that I have to search between index 0 and 6 because index 7 is greater. So I find the next middle, that is index 3. I just go and search there. I go and search there, and I see that this one is smaller than 33. So what does it mean? It means that nothing here on the left can be 33, right? So I discard this, and immediately you see that now my search space has shrunken even by half, right? So it's n over 2. So this is the part where I have to search, right? Okay, then I know that I have to search between index 4 and 6. So the middle is index 5, I go there, and this is still large. That means there is no chance that 33 is here, right? So I discard that. Now you see my search space has become n over 2 over 2. So basically my target is I have reached 1, a search space of 1. That means I have found my value, right? Okay, so you see how the binary search is being done. It's a divide and conquer algorithm. We look for the key in the middle. If we get a match, then the search is over. If the key is greater than the thing in the middle of the list, we search the top half or the right side, right? Right half. If the key that we were searching, suppose we were searching 33, is smaller than the middle element, we search the bottom half or the left half. That's exactly what I showed you, right? And what was the time complexity? You see that initially the search space was n, then it shrink to n over 2, then it shrink to n square, and then finally it went up to 1, right? So how many steps are here? It's log n. So can you see that? So the time complexity of binary search is order of log n. So you see how better this is in compared to the linear search time complexity of order of n.